So mechanical properties of fluid. So first thing, in this chapter we are going to learn pressure and what are the behavior of fluids, different laws and their applications we'll see in this chapter. But before we go, we have to create some foundation before we can proceed. Let's start with the pressure. What is pressure? That would be better. So let's start with the pressure. What is pressure? Pressure, as you know, is defined as force per unit area. What is this SI unit? SI unit of force is, pressure is Newton per meter square, also known as Pascal. This is after the physicist who has given the Pascal's law, which we are going to learn within few minutes. Now this is Pascal, so also known as Pascal. Now pressure, here in this chapter we are going to focus mostly on air, liquid, different kind of other substances. But what are some example of pressure? Let's see, which we are going to frequently come across is, first of all, what is the air pressure? 1 atm. Some different units of pressure. Let's see. Units of pressure which we are more interested in this chapter would be 1 atm. 1 atmospheric pressure. 1 atm means, or 1 atmospheric pressure. What is 1 atmospheric pressure? It is defined as 1.013 into 10 to the power 5 Pascal. 5 Newton per meter square, or simply Pascal. Okay? Or you can write 1 bar. 1 bar is 10 to the power 5 Pascal. So you can also write this as 1.013 10 to the power 5 Pascal. Now another way we can write this, 1.1013 into 10 to the power 5 divided by 1000. If I do, then I get here, I will remove 2 zeros from here, one zeros from here, then I get here 4, one more zeros, so I get here 101.3 kilopascal. This also you can write. Okay, so actually, or another way, you can write this 1 atm as 101.300 Pascal. These are different way of writing the 1 atm. Or what is 1 atm? It is the atmospheric pressure. The pressure exerted by the atmosphere on the surface of the earth is the 1 atmosphere, or 1 atm. But these do not express anything. You can't understand anything from this, what is actually, how much is the pressure. So other units of pressure is PSI, or pounds per square inch. Pound per square inch. Now pounds per square inch, or PSI, if you have a vehicle, you will see in your vehicle the air pressure of the tire, the tubes of the wheel tube or the tires are in PSI. They are not in atm. So what is 1 atm in terms of PSI? So 1 atm is equals to 14 PSI, or pounds per square inch. Means within a 1 square inch there is a 14 pound of pressure exerting on a 1 square inch. This means that. So 14 PSI is equals to 1 atm. So you can also use this to establish another relation. So 14 PSI is equal to, I can write 1.013 into 10 to the power 5 Pascal, which you can also write 101.3 kilopascal. So if I solve this 14 PSI, so if I solve this one, so 1 PSI will be how much? Let's see. So 1 PSI will be 101.3 into 10 to the power 3 divided by 14. So if I divide this one, I get this around 101.3 divided by 14. I get approximately 7.2 kilopascal. So this is 1 psi, 1 pounds per square inch, approximately, that is approximately 7 kilopascal. Now, so you can understand that within a 1 pound per square inch, 1 square inch, there is how much of pressure? Now within 1 square inch, okay, you can see we are having a 7.2 kilopascal amount of pressure acting on that within that area. So this is how large is it, how big is it, you will see gradually as we progress. So now let us come to density before we proceed to the Pascal's law. So these are different units of pressure. I must tell you here also one more thing is there, 1 bar. 1 bar also sometime, which is nothing but this 10 to the power 5 Pascal is known as 1 bar, 10 to the power 5 Pascal. So sometime we can also write 1 atm as, so 1 atm can also be written as 1.013 bar. So these are different units. So how many units we have been able to identify? We have seen Pascal or Newton per meter square, or we have seen pounds per square inch. Okay, then we have seen bar. These are another unit of pressure is there, which we see by using a particular device, which is an application of Pascal's law, which we will see. We will learn that how to get that 1 atm is equal to. So another unit, for now you know, the another unit of pressure is 76 millimeter of mercury. So we can also write 1 atm as 760 millimeter of mercury, Hg, or 76 centimeter of mercury. So these are all units, different units. All these units will have to use in this all these units will be using in this chapter. So it is very, very important. Okay, so 76 centimeter or 760 millimeter of mercury, this would be used mostly in case of fluid. You see, when you go for air pressure, when you take your BP, blood pressure, it is expressed in this value, 76 millimeter of mercury. How much is it? It is compared with this one. Now when you go for some kind of hydraulic motion, hydraulic thing where liquids are used to create hydraulic pressure and all, then this unit will be Pascals will be used. And when you are going for putting air in valve, air in tubes, then definitely PSI is used. So all these units has their significance, and while doing it you always have to stay in SI metric system, or else the system will get, so you'll get trapped into the conversion system. That's why I'm giving a full conversion chart on pressure. Similarly, now let us see density. What is density? As you know, we'll see some density of some material which is very useful for us. Density. So density is, as you know, mass density is mass per unit volume. So its SI unit would be what? kg per meter cube. CGS gram per centimeter cube. Now 1 centimeter cube is actually also equal to milliliter. 1 centimeter cube in terms of liquid is 1 milliliter. Therefore, we can write this as gram per milliliter. So try to imagine, if we see the density of water, let us see what is the density of water. So density of water is quite very large. Okay, is 1 kg per meter. So if you imagine a cube of size 1 meter size, 1 meter, a water cube of side 1 meter, all along. So density of water is 1000 kg per meter cube. So how will you convert this into gram? So you can easily convert this into gram as 1000 kg into 1 kg equals to 1000 gram. So again 1000, and 1 meter equal to 100 centimeters. So 100 into 100 into 100. So 2 gone. Again 1 goes from here. So 1000. You can see it goes. It is actually 1 gram per centimeter cube. So 1 gram per centimeter cube. So density of water is actually very large. So you can imagine that a cube of density of water whose density is 1000 kg per meter cube. So a cube of 1 meter is very heavy. Water 1 meter you cannot. It is perhaps in 1000 kg is 1 ton. Right? In 1 meter cube, the mass is 1000 kg, 1 ton. So we cannot lift. It is so heavy if you take 1 kg. That's why another unit of will be 1 gram per centimeter cube. Now density of seawater, which we'll be using. Density of seawater is generally little bit more. So 1030 kg per meter cube. That's why it is easy for you to swim in sea water. Why? Archimedes principle is present there. We'll see. So 110, that means it is actually again 1 gram. So if we remove this, I get here 1.03 gram per centimeter cube. Okay. Then density of normal oils, which you see, household cooking oil and oil. Oil generally is between 500 to 800 kg per meter cube. Now density of other materials, for example, density of gold. Density of gold or AU is around 19.3 into 10 to the power 3 kg per meter cube. Density of mercury, which we will be using very oftenly, density of Hg or mercury is 13.6 into 10 to the power 3 kg per meter cube. Now another material. So other, as you go, it is keep increasing. It is increasing. You can see density of, for example, I will see density of platinum. It is density of platinum PL, I think PT is 21 into 10 to the power 3 kg per meter cube. The most important one which we see, what is air? What is the density of air? Density of air will be 1 point. Now is air very dense or very thin? Definitely density of air is very thin because it is a gas. It is moving around everywhere. So what is the density of air then? it is 1.29 kg per meter cube, which you can write this as, you see, very thin. Compare with them. So air is very thin. So 1.29 kg per meter, which is nothing. If you write it in gram, it would be 0.00129 gram per centimeter cube. So there are many other density material, but these are the most thing which you are going to use it. So if you want to be very good in this chapter, very strong in this chapter, play with density is very important. So remember all these densities thoroughly. You have to keep this in mind, keep this in your, you have to memorize these densities. For example, mercury, 13.6 in 10 to the power 3 kg per meter cube. So, and then this one, 10 to the 3 kg per meter cube. What is 10 to the 3 kg per meter cube? It's nothing but 1 gram per centimeter cube. So you can also write this as 13.3 gram per centimeter cube. This would be 19.3 or 19.3 gram per centimeter cube, and so on. Similarly, this is 0.8 gram per centimeter cube, and so on. So we're going to play with different units in this chapter. So that's why I'm giving this. Now let us come to Pascal's law. Pascal's law. But before I come to Pascal's law, we must understand what is an incompressible liquid. Incompressible liquid. What do you mean by this? A liquid is said to be incompressible if its bulk modulus is infinite. A liquid that is, its bulk modulus is infinite means there is no change in its, the change in its volume is zero. A liquid, wait, we'll write it first. So, incompressible liquid. A liquid is said to be incompressible if there is no change in volume when infinite compressive force under infinite compressive stress is acting over it. That is, the bulk modulus of the liquid, the bulk modulus of the liquid is infinite. So we know what B equals to, this is the compressive stress divided by change in volume by volume. So if this is V is 0, delta V is 0, so what do we see? It becomes 1 by 0. That is, bulk modulus is infinity. So such a liquid is called incompressible liquid. So based on this, if we consider such kind of liquid, Pascal's law is given on such kind of liquid in which the bulk modulus, it is liquid is incompressible. You cannot compress it, you cannot decrease its volume. For such liquid, if a pressure applied to one part of the liquid is uniformly distributed throughout the rest portion of the volume of the rest of the portion of the liquid. This is Pascal's law. So what does the Pascal's law states?
So can you go to the previous page once the last part of that?
Yeah.
So what is written in the last one, infinity? So that infinity one.
B equals to infinity. Bulk modulus is equal to infinity. The bulk modulus of the liquid is infinity. I know I have written so badly here. It's not clear. Bulk modulus of the liquid is infinity.
Okay.
So, can you give me an example? Is water is example of incompressible liquid? Is water an incompressible liquid? Can you compress water? Can you compress it to decrease its volume? If you put it in a chamber, put it in a cylinder, and with a piston, if you are compressing it, will you be able to decrease its volume in that cylinder? Have you thought about it? Can you decrease it?
No.
So Pascal's law is based on such. Water is an incompressible liquid. Okay? So Pascal's law. According to Pascal's law, let us understand this situation first before we can apply the Pascal's law. Understand Pascal's law. Let us draw one diagram here. This is a sphere of some sort. We have cylinders fitted here. So cylinders is fitted here, and this is filled with liquid. Okay, so if a force is applied on this, if a force is applied in any one of the cylinder, if it is been compressed, what do you expect will happen? What do you expect will happen? This is a sphere fitted with 4 pistons. Pistons means they are easily movable over this small little these cylinders. They can move very freely. They can go out. They can move very freely over this. So if any one of this sphere, one of the cylinder, one of the piston, they are called pistons. These are called piston, and this is the cylinder. This is the cylinder, and if you push this piston, what will happen to the remaining 3? Will they also be expanded out? Will they also come out equally, or only this one will come out? Or maybe this one will not come out, only this one and this one will come out. Which one? What do you think? What do you think? All the 3 will, all the three will expand out uniformly. Got it? The pressure the pressure that you exert on this cylinder, that we name this cylinder 1, 2, 3 and 4, the pressure what you exert on the cylinder 1 will be transmitted equally in all the three. Understand? So as a result, they will all come out with uniformly. They will move out uniformly by the same displacement. This is called the Pascal's law. So Pascal's law states, according to Pascal's law, pressure exerted at any point on an enclosed incompressible liquid is transmitted equally in all direction. Is transmitted equally in all direction. This is Pascal's law. So based on this Pascal's law, we can find out the pressure at different regions. Okay, so this is our Pascal's law. We'll use this Pascal's law now in finding out what is the pressure at different places. Let's establish an expression for pressure in terms of atmospheric pressure. Let us see that now. So let's say you have a column of liquid. Pressure variation with height or h. Let's see. Although we'll come to Pascal's law once again in hydraulic pressure, but right now we've got a little bit of idea of what Pascal's law says. So consider a liquid column. A column of liquid, let's say an air. So you consider a liquid column like this. This is a liquid column of air. Maybe a fluid column. A fluid column. Its height is h. Height is h. Cross-sectional area is A. Cross-sectional area of this portion is A. What do I mean is this? How I am taking this liquid column? Imagine in your room Imagine in your room where you are sitting, you consider an imaginary liquid column, a cylindrical cubical column of air. That is what we are considering. His height is h and base is has a cross-sectional area of a. An imaginary column, that's it. So what is the force at the top? So this is the force acting here, or also this column is under the pressure, also under the force, or under the pressure from all sides. Pressure, this is the pressure at the top, this is the pressure at the bottom, right? Because it is under the pressure from all sides. Only there is a difference in height. These two sides, they will be equal and opposite. So there is nothing much importance here. But what is important here is based on the height. So what do you think will be pressure at the bottom will be? So we can see that. Also, if you look at the weight of this liquid column, so what is the force? If you see in terms of force, what is the force acting? So this is the force acting due to the weight of the liquid above the column, right? And this is the, so this is the force at the top, and this is the force acting on the bottom. And also it has its own weight mg, right? Therefore we can write like this: consider a liquid column of height h and cross-sectional area A. The forces acting on this column, forces acting on this column's base surface or at the bottom is force at the bottom will be equal to force at the top plus its own weight mg. Okay, therefore if I divide by area, so this become F by A, FB by A is equal to Ft by A plus mg by A. Now this is nothing but pressure. Pressure at the bottom equal to pressure at the top plus mga, but this is mass by area, right? We know density of the liquid, density rho equals to is the density of this incompressible liquid which you can write this as mass by volume, or you can write this as mass by area into h, implies m by a. What can you write? M by a can be written as rho into h. So if I plug this here, use this relation over there, I see that density rho is equal to pressure at the bottom is equal to pressure at the top plus h rho g. This is the pressure acting at the bottom face of a liquid column of height h. Okay, liquid column of height h. Let us try to understand with an example. then it would be clear. If I give you a, let's say this is ocean surface, a swimmer is swimming 10 meter below sea level. This is the sea level, and someone is swimming at the 10 meter below sea level. So find the pressure acting on the swimmer swimming acting on the swimmer swimming 10 meter below the sea level. 10 meter below the sea level. That's excellent. So what else do you need? Do you know everything to answer this? You see, no other data is given. Only 10 meters is given to you. How will you solve this? You see here, the top pressure is P atm, atmospheric pressure. What do you need to know? We need to know what is the pressure of the volume of liquid at this point. That is at a depth. So depth from where? Depth from this point. How much is it from here? So this is the pressure at the bottom. Therefore we can write pressure at the bottom will be equal to pressure at the top plus H rho g. You must remember it like this. Pressure at the bottom is equal to pressure at the top plus H rho g. I'm not going along with any reference book, not going along even with NCERT also. But this is the best way to tackle this paper. So pressure at the top is what? 1 atm plus H. H is how much? 10. And what is this liquid? Is C. C is 1030 kg per meter cube. I gave you that's why I gave you the density chart in the beginning. Okay, so it is 1030 into 1030 kg per meter cube. Okay, so let us do this everything in SI unit system. So it is 1 atm. Remember, it's 1 atm plus H rho g. Let me take g as 10 for our purpose. So pressure at the bottom is equal to pressure at the top. Pressure at the top is how much? 1 atm plus H. H is how much? 10. And rho is how much? Density is this and g is 10. Therefore 1 atm is how much? Go back and let us see this. It is actually 101300. I am going to use like this. This is in direct kg per meter cube. I taught you that 1 atm is equal to 1.013 into 10 to the power 5 Pascal. So which you can write 101300 plus how much here again? 10300. So if you add them, how much you get? 101300 plus 1000301. So I get here 00, then 6111, 116 111 600 00 Pascal. 00 Pascal, but no use. I cannot understand anything. How much atm is it? Now 1 atm is 1.01, or no, I'll write like this way. That would be easier then. It would be easier like this. 1 atm is 101300 Pascal. So this much Pascal, so 1 Pascal is equal to 1 by 101300 atm, right? Therefore what you can do, 1 Pascal will be, so 101300 Pascal will be how much? 101300 divided by 101.101300. No, what I am doing? I need to convert this. No, sorry. It is 111600. 111600 Pascal is equal to 111600. So cancel this. Now if I divide them, if I divide this 1116 divided by 1013, that gives me around 1.101 atm, little bit more than 1 atmosphere as you go 10, right? So this is how you can find the pressure at the bottom of a lake. Similarly, you can find at the top. We'll do that in the, after knowing some of the topic, we will do that, what is the pressure at the top. So I'm giving a homework which you can try. Find the pressure acting on the deepest point on the earth, that is the Mariana Trench. Mariana Trench, (11,000 meter below sea level. 11,000 meter below sea level. Compare this result in terms of ATM and PSI per square inch acting on the surface. Acting on the surface of the, acting on the surface, zero sea level. Okay?
Yes.
One more question. A submarine is diving 500 meter below sea level. It has windows of dimension (1 meter). Windows of dimension of 1 meter. 50 centimeter into 50 centimeter. Find the pressure exerted on the glass pane of these windows.